You've watched flames dance, you've felt their heat on your skin. You've seen smoke curl upward into the sky. Fire is everywhere in human history. We've used it for hundreds of thousands of years to cook food, forge metal, and light the darkness. But here's the strange thing. Most people have no idea what fire actually is. Ask someone to explain fire and they'll tell you it's hot. It burns things. It needs fuel and oxygen, but that's like describing a car as something that moves and needs gas. You're describing what it does, not what it is. The truth about fire is far stranger and more elegant than you might imagine. Fire isn't really a thing at all. It's not an object. It's not made of matter in the way a rock or water is made of matter. Fire is a process, a chemical reaction that you can see, and when you understand what's actually happening at the atomic level when something burns, you unlock one of nature's most beautiful secrets. Let me take you on a journey into the heart of combustion. The puzzle of the patient would imagine a log sitting in your backyard. It's been there for months, maybe years. Rain falls on it, sun beats down on it, air surrounds it constantly, and nothing happens. The wood just sits there, unchanged, patient, waiting. Now think about what that wood is made of. It's mostly carbon atoms, arranged in long chains called cellulose, bound together with other organic molecules. The air surrounding the wood is about 21% oxygen. These oxygen molecules are constantly bouncing around, moving, colliding with the wood's surface billions upon billions of times every second. Here's what's bizarre. Those carbon atoms in the wood and those oxygen atoms in the air desperately want to join together. When carbon and oxygen bond, they form carbon dioxide, and this bonding releases a tremendous amount of energy. The carbon-oxygen bond is one of the most stable configurations in chemistry. Carbon and oxygen together is a low-energy state. It's where these atoms want to be, so why doesn't the wood just burst into flames spontaneously? The answer lies in something chemists call activation energy. Think of it like this. Imagine two lovers separated by a tall wall. On one side stands carbon, on the other side stands oxygen. They're attracted to each other. Being together would release energy. That's the stable state they're trying to reach, but between them is this wall, this energy barrier. The atoms are constantly colliding. Oxygen molecules slam into carbon atoms millions of times per second. But these collisions are like someone throwing a ball at the wall. It just bounces back. The atoms hit each other, but they don't have enough energy to overcome the barrier. They collide and separate, over and over, achieving nothing. This can continue for years, decades, centuries even. Wood can sit exposed to air for 1,000 years without burning because those atoms, despite their mutual attraction, can't get over that activation energy barrier. The spark that changes everything. Now you strike a match and touch it to the wood. What are you actually doing? You're not creating fire. You're not adding some magical fire element to the equation. All you're doing is adding energy, heat energy specifically. That heat makes atoms move faster. Temperature, at its most fundamental level, is just a measure of how fast atoms are vibrating and jiggling around. When you heat up a small region of the wood with your match, you're making those carbon atoms vibrate more violently. You're making the oxygen molecules that hit them move faster with more force, and eventually some of these collisions are energetic enough to get over that wall. When a carbon atom and an oxygen molecule finally have enough energy to overcome the activation barrier, something wonderful happens. They bond. The carbon and oxygen snap together, forming carbon dioxide or carbon monoxide. And when they snap together, they release energy. This is the crucial point. The bonding process releases more energy than it took to get over the barrier. The atoms had to climb up an energy hill to react, but once they do, they fall down an even deeper energy valley on the other side. That released energy doesn't just vanish. It has to go somewhere. And where does it go? It goes into heating up the surrounding atoms, making them vibrate faster, giving them more kinetic energy. Now those heated atoms have enough energy to react too. So they bond with oxygen and they release more energy, which heats up more atoms, which react and release more energy, which heats up even more atoms. Do you see what's happening? It's a chain reaction. It's exponential growth. One reaction triggers 2 to trigger 4 for trigger 8. The number of reactions doubles and doubles. And doubles. Within fractions of a second, you go from a handful of reactions to billions of simultaneous reactions. This is why fire doesn't start gradually. It explodes into existence. One moment nothing is happening, the next moment, flames. That sudden appearance isn't magic, it's mathematics. It's exponential growth, a runaway feedback loop. This cascade of atoms snapping together, releasing energy, causing more atoms to snap together. This is fire. Fire is this chain reaction made visible. What you're actually seeing. So what exactly are flames? What are you looking at when you see fire? Flames are glowing gases. When atoms and molecules get hot enough, when they're jiggling fast enough, they start to glow. More precisely, the electrons in those atoms absorb energy and jump to higher energy levels. But those higher energy levels are unstable, so the electrons quickly fall back down, and when they do, they emit light, photons. That's the glow you see. Different atoms emit different wavelengths of light, which means different colors. The yellow-orange color of most wood fires comes primarily from glowing soot particles, tiny bits of carbon that get hot enough to glow but don't fully combust. The blue you sometimes see at the base of a flame is from carbon monoxide and other gases burning at higher temperatures. Add certain elements and you get different colors entirely. Sodium burns yellow, copper burns green, lithium burns red. This is why fireworks work. Different chemical compounds produce different colored flames when they burn. The smoke you see rising is a mixture of things, some of it is water vapor. Remember, when organic materials burn, the hydrogen they contain combines with oxygen to form water. Some is carbon dioxide, which is invisible. And some is particulate matter, tiny solid particles of carbon and other materials that didn't fully combust, floating upward because they're hot and less dense than the surrounding air. The heat you feel radiating from a fire is infrared radiation, electromagnetic waves carrying energy away from the hot gases. The fire also heats the air directly through conduction, and that hot air rises and flows, creating the characteristic upward movement of flames. The fire triangle. Fire requires 3 things, often called the fire triangle: fuel, oxygen, and heat. Remove any one of these and fire cannot exist. The fuel provides atoms that want to bond with oxygen, usually carbon and hydrogen in organic materials, but many other substances can burn too. Metals can burn, even ice can burn if you add enough energy and the right oxidizer. Oxygen is the other half of the equation. Something has to accept those electrons, and oxygen is very good at it. Oxygen is what chemists call an oxidizer. It readily accepts the electrons from other atoms. That's why rust forms on iron, why apples turn brown when you cut them, why batteries eventually die. Oxidation is happening everywhere, constantly. Fire is just oxidation happening very, very fast. Heat provides the activation energy to get reactions started and then sustains the chain reaction by keeping atoms moving fast enough to continue reacting. This is why you can extinguish fire in different ways. Pour water on it, and you cool it below the threshold temperature. You break the chain reaction by removing heat. Smother it with a blanket, and you cut off the oxygen supply. Remove the fuel by creating a fire break, and you stop it from spreading. Each method breaks a different leg of the triangle, and without all 3 legs, fire cannot stand. The great cycle. Now let's zoom out and see the bigger picture, because this is where it gets truly beautiful. Where did that wood come from? From a tree? obviously. And where did the tree come from? Most people would say the ground. The tree grew in soil, so clearly it came from the soil, right? This seems like common sense. You plant a seed in dirt, the tree grows. Therefore, the tree is made of dirt, but this common sense is completely wrong. Here's an experiment that will prove it. Take a large pot and fill it with exactly 100 pounds of soil. Weigh it carefully. Now plant a seed and water it regularly for 5 years. Let the tree grow. After 5 years, carefully remove the tree and weigh it. Let's say it weighs 80 pounds. Now dry the soil completely and weigh it again. The soil will weigh almost exactly 100 pounds, maybe 99 pounds if the tree absorbed some minerals. But the tree weighs 80 pounds. Where did those 80 pounds come from? It didn't come from the soil because the soil barely lost any weight. This experiment was actually performed by a Flemish physician named Jan Baptist van Helmont in the early 1600s. He grew a willow tree in a pot of soil for 5 years. The tree gained about 164 pounds. The soil lost only 2 ounces. Van Helmont concluded that the tree must have come from the water he added. He was partly right. Water is indeed part of the tree's mass. But most of the tree's weight, that carbon that makes up the bulk of its structure, came from the air. Trees are made of air. More specifically, trees pull carbon dioxide out of the atmosphere. Through photosynthesis, they use energy from sunlight to break those carbon dioxide molecules apart, keeping the carbon and releasing the oxygen. That carbon becomes the structure of the tree, the cellulose, the lignin, all the complex organic molecules that make up wood. Think about how remarkable this is. A 100-foot tall oak tree, weighing many tons, is built primarily from invisible gas pulled out of the air. The tree is essentially solidified air held together by energy from the sun. The sun's hidden role. This brings us to the most poetic part of the story, the role of sunlight. Remember how I said carbon and oxygen want to be together? Carbon dioxide, carbon bonded to oxygen, is a very stable, low-energy configuration. So how does a tree manage to rip those molecules apart? How does it overcome that stability? With energy. From the sun, photosynthesis is essentially the opposite of fire. Fire takes carbon and oxygen that are separated and snaps them together, releasing energy. Photosynthesis takes carbon and oxygen that are bonded together and rips them apart, which requires energy. That energy comes from photons of sunlight. The tree is using light energy to do work, chemical work. It's forcing molecules into a higher energy state, a less stable configuration. It's like pushing a boulder uphill. The carbon and oxygen want to roll back together, but the tree is holding them apart. And here's the beautiful connection. When you burn that wood, you're reversing the process. The carbon that the tree worked so hard to separate from oxygen is snapping back together. The energy that was stored in that separation, the sunlight, energy that went into pulling carbon dioxide apart, is being released. Fire is stored sunlight. Every flame is a release of solar energy that was captured months or years or decades ago. The warmth you feel from a campfire is warmth that fell as sunlight on leaves years ago, was captured by chlorophyll, was used to build structure, and is now escaping as those structures collapse back into carbon dioxide. You're watching the sun shine again, in a sense. Delayed sunshine, banked solar energy being withdrawn all at once. Fire in your body. Here's something that should make you pause. You are burning right now. Inside every cell in your body, tiny structures called mitochondria are performing combustion. They're taking sugar molecules and combining them with oxygen to release energy. The process is called cellular respiration, and it's exactly the same chemistry as fire. Glucose plus oxygen yields carbon dioxide, water, and energy. That's fire. That's also what your cells do every moment of every day. The only difference is control. Your cells burn fuel slowly, carefully, capturing the released energy in molecules called ATP that can be used for cellular work. Fire burns fuel all at once, releasing energy as heat and light that radiates away, but the fundamental chemistry is identical. Your body is running on controlled combustion. You are, in a very literal sense, a slow fire. The oxygen you breathe in is combining with carbon-based molecules from your food, releasing energy that powers everything you do. And just like fire, if you remove one element of the triangle, the process stops. Cut off oxygen and you suffocate, remove fuel by not eating and you starve. Lower your temperature too much and your metabolism shuts down. The carbon dioxide you exhale is the same waste product as fire. Carbon and oxygen reunited, returning to the atmosphere where plants will pull them apart again using sunlight to build more structure. It's a cycle, a vast global cycle. The oxygen story. Let's talk about that oxygen you're breathing, because its existence is one of the most remarkable things about our planet. Earth's early atmosphere had essentially no free oxygen. It was mostly carbon dioxide, nitrogen, water vapor, and various other gases. Oxygen is highly reactive. It wants to bond with things. Any free oxygen would quickly react with rocks, dissolved metals, and other materials. For oxygen to exist in the atmosphere in large quantities, something must be constantly producing it. That something is photosynthesis. About 2.4 billion years ago, certain bacteria evolved the ability to use sunlight to split water molecules, releasing oxygen as a waste product. These cyanobacteria began pumping oxygen into the atmosphere. For them, oxygen was toxic waste. They didn't use it, they just got rid of it. The oxygen initially combined with dissolved iron in the oceans, forming rust that settled to the ocean floor. Those ancient rust layers are visible in rock formations today, literal stripes of red in ancient stone, marking the moment oxygen began flooding into Earth's environment. Eventually, the oxygen saturated the oceans and began accumulating in the atmosphere. This was catastrophic. For most existing life, oxygen was poisonous to the anaerobic organisms that had evolved in an oxygen-free world. There was a mass extinction event called the Great Oxidation Event, but some organisms evolved to not just tolerate oxygen, but to use it. They developed ways to burn fuel with oxygen, extracting far more energy than anaerobic processes could provide. These became the ancestors of all oxygen-breathing life, including you. So the oxygen in the air, the oxygen that makes fire possible, the oxygen you breathe is ancient waste. It's the accumulated garbage of countless photosynthetic organisms over billions of years. And it's also one of Earth's most valuable resources, enabling both fire and aerobic life. Why things don't spontaneously combust. Let's return to a question that should be bothering you. If carbon and oxygen release so much energy when they bond, and if there's carbon and oxygen everywhere, why doesn't everything just spontaneously burst into flames? The answer is that activation energy barrier again. At room temperature, atoms and molecules are moving, but not fast enough. They're jiggling and bouncing around, but most collisions aren't energetic enough to trigger reactions. The world is full of what scientists call metastable states, systems that want to release energy but can't get started on their own. A log in oxygen, gasoline and air, the food in your pantry and the oxygen in your kitchen. These are all high energy states waiting for a trigger. This is actually a good thing. If activation energy barriers didn't exist, the world would be impossible. Materials would spontaneously combust, food would instantly oxidize. Life couldn't exist because organic molecules would constantly be reacting and breaking down. The activation energy barrier acts like a gate, allowing molecules to exist in high energy states until something provides the kick needed to get reactions started. That kick might be heat from a match. It might be a spark of electricity. In your cells, it's enzymes, biological catalysts that lower the activation energy, making reactions possible at body temperature. Catalysts are crucial. They don't change the overall energy of a reaction. They don't make carbon and oxygen release more or less energy when they bond. What they do is lower the activation barrier, making it easier for reactions to get started. Your body is full of enzymes acting as catalysts, enabling thousands of different reactions to proceed at reasonable rates. Without enzymes, the reactions in your body would be impossibly slow at normal body temperature. With enzymes, those reactions happen at rates that can sustain life. The varieties of fire. Not all fires are the same. The nature of the fuel determines how the fire burns. Wood burns relatively slowly because cellulose is a large, complex molecule that takes time to break down. The fire has to heat the wood enough to break apart those large molecules into smaller pieces that can more easily react with oxygen. This is why you see smoke and flames above burning wood. Complex molecules are being broken apart into smaller, volatile compounds that drift upward and burn in the air above the fuel. Gasoline burns much faster because it's already made of relatively small, simple molecules that react quickly with oxygen. This is why gasoline is dangerous. It vaporizes easily, mixes with air, and can ignite explosively. Hydrogen burns even faster with a nearly invisible flame. Hydrogen combines with oxygen to form water, releasing energy. The flame is so hot that it produces very little visible light in the wavelengths we can see, though it glows brightly in ultraviolet. Metals can burn too, given enough energy. Magnesium burns with an intensely bright white flame, hot enough to weld with. Steel wool will burn if you light it with a flame or pass an electric current through it. Even ice-solid water can undergo combustion under extreme conditions if you have the right oxidizer. The common thread is that all these processes are oxidation reactions releasing energy. The fuel combines with an oxidizer, forms more stable products, and releases energy as heat and light. Fire and civilization. Humans' relationship with fire fundamentally changed our species. Control of fire allowed our ancestors to cook food, which made nutrients more accessible and reduced the energy needed for digestion. This may have enabled the development of our large, energy-hungry brains. Fire provided warmth, allowing humans to inhabit colder climates. It provided protection from predators. It extended the day, giving more time for social interaction and tool making. Fire enabled metallurgy. You can't smelt ore or forge metal without high temperatures. The entire Bronze Age and Iron Age were built on our ability to make things very hot using combustion. Fire powered the Industrial Revolution. Steam engines burned coal to heat water, creating pressure that drove pistons. Internal combustion engines burn gasoline or diesel to create expanding gases that push pistons. Jet engines burn fuel to create hot, expanding exhaust gases. Even today, most of our electricity comes from burning fuel: coal, natural gas, oil to heat water into steam that turns turbines. We are a species that has yoked fire to our purposes. We've learned to start it, control it, shape it, and use it to transform raw materials into useful products. Our technological civilization is built on controlled combustion. The limits of fire, but fire has limits. Not everything can burn because not everything has a favorable reaction with oxygen. Noble gases like helium and neon don't react with anything under normal conditions. Their electron shells are complete. They don't want to gain or lose electrons. They're inert. Carbon dioxide and water are already the products of combustion. You can't burn them because they're already in a low energy state. The carbon and oxygen are already together. The hydrogen and oxygen are already together. There's no energy to be gained by reacting them. Further, some materials are flame retardant because they absorb heat, making it harder for fire to sustain itself. Materials like concrete and gypsum contain water molecules locked into their crystal structure. When heated, this water is released, absorbing energy and cooling the material. Some materials release gases that exclude oxygen or interfere with the chain reaction. This is how many chemical fire retardants work. They don't make things non-flammable. They make it harder for fire to spread by disrupting the combustion process. Beyond Earth fire, as we know, it cannot exist in space. There's no oxygen in the vacuum of space, so conventional combustion is impossible. But stars are, in a sense, cosmic fires. They're not burning in the chemical sense, they're not oxidation reactions instead. They're running on nuclear fusion. Hydrogen atoms are being smashed together under enormous pressure and temperature, fusing into helium and releasing vast amounts of energy. This is a different kind of reaction entirely, but there are parallels. Like chemical fire, fusion reactions require activation energy. You need enormous temperatures and pressures to get hydrogen nuclei close enough to overcome their mutual repulsion and fuse, and like chemical fire, once fusion starts, it sustains itself by releasing energy that maintains the high temperatures needed for more fusion. The sun is powered by nuclear fusion converting hydrogen to helium. That energy radiates outward as light. Some of that light reaches Earth, where plants use it to rip apart carbon dioxide. That carbon becomes wood. Later, we burn that wood, releasing the stored energy. Fire connects to stars. The warmth of a campfire is an echo of nuclear fusion in the sun's core, transferred through photosynthesis and stored in chemical bonds, then released again when we strike a match. The philosophy of fire. Ancient peoples didn't understand fire, but they recognized its importance. Many cultures considered fire one of the classical elements: earth, water, air, and fire, fundamental substances from which all else was made. This was wrong, of course. Fire isn't an element or a substance, it's a process. But the intuition wasn't entirely off base. Fire does represent something fundamental about how the universe works. Fire is about energy transformation. It's about systems moving from higher energy states to lower energy states, releasing energy in the process. This principle that systems naturally move toward lower energy configurations is one of the most fundamental laws of physics. Fire is also about order and disorder. The tree represents order, complex molecules arranged in intricate patterns. When it burns, that order is destroyed, and the complex molecules become simple gases. This is entropy increasing, which is what the second law of thermodynamics tells us must happen in closed systems. But zoom out further, and you see the larger cycle. The disorder of combustion is countered by the ordering work of photosynthesis. The sun provides energy that plants use to create order from disorder, to build structure from simple gases. Then fire releases that structure back into disorder, and the cycle begins again. Neither process violates thermodynamics because energy is flowing into the system from the sun. The sun is slowly exhausting its fuel, increasing universal entropy even as it allows local decreases in entropy here on Earth. What fire teaches us. Understanding fire reveals fundamental truths about chemistry, energy, and life. It teaches us that the world is built on attractions and repulsions, on atoms wanting to bond in certain ways. The whole of chemistry is about electrons, how atoms share them, donate them, accept them. Fire is a visible manifestation of electron transfer happening at a massive scale. It teaches us about energy barriers and how systems can get stuck in metastable states. This principle applies far beyond fire. Chemical reactions in industry, biological processes in cells, even economic and social systems can get stuck in stable but not optimal states, requiring activation energy to transition to better configurations. It teaches us about chain reactions and feedback loops, how processes can explode exponentially once they get started. This applies to fires, but also to nuclear reactions, to epidemics, to viral ideas spreading through populations, to financial bubbles and crashes. It teaches us that energy flows and transforms but never disappears. The energy in fire came from the sun, was stored in chemical bonds, and is released as heat and light that radiates away, eventually becoming waste heat. Energy is conserved, but it flows from concentrated to dispersed, from useful to less useful. And it connects us to the cosmos. The carbon that trees pull from the air was forged. In ancient stars, the oxygen we breathe was produced by billions of years of photosynthesis. The energy in fire originated in nuclear fusion in the sun's core. Fire connects atoms to energy, life to light, trees to stars. The final questions. We've covered a lot, but there's always more to ask. How exactly do flame colors work at the quantum level? What's happening with the electron orbitals and energy? Transitions. How do you calculate the heat of combustion for different materials? What determines whether combustion will be explosive or gentle? Why do some materials burn cleanly while others produce toxic smoke? How do fire suppressants work at the molecular level? What's the chemistry of spontaneous combustion in hay or oily rags? And the biggest question of all, the one that pushes us beyond fire to something even more fundamental: where does the sun's energy come from? How does nuclear fusion work? Why do atomic nuclei contain so much energy in the first place? That's another journey, another story. Fire has led us to the doorstep of nuclear physics, to the hearts of stars, to the origin of atoms themselves. But that's where I'll leave you for now, at the edge of understanding, with questions still unanswered, ready to explore deeper. Because that's what fire teaches us in the end. Everything connects. Pull on one thread and the whole tapestry begins to reveal itself. Start with a simple flame and you end up contemplating the nature of atoms, the history of life, the physics of stars. Fire is simple and fire is profound. It's as close as a candle and as distant as the sun. It's in your cells and it built your civilization. Now you know what fire really is. Not just something hot that destroys things, but a window into the fundamental workings of matter and energy. A visible manifestation of chemistry in action. A link between sunshine and structure, between life and light. The next time you see flames, you'll understand what you're really watching: atoms rushing together, releasing ancient sunlight, participating in the great cycle that connects stars to trees to fire to life. That's the truth about fire, and it's more beautiful than any myth.